So the first section of chapter 29, 29.1, we just start to we start to it starts to explain the formalism before we get into the reasons, which it seems a little backwards to me. Do you remember a couple of weeks ago when I said that finally we're in the 20th century? Yeah. So this chapter covers stuff that was put forth between 1905 and 1918. So we're still more than 100 years away from the present, and of course we're not covering anything, but at least we're covering some topic that can, at least in some sense, be called modern. So let's start with section 29.2. This is actually a really important experiment. This is a kind of experiment that was actually done starting in 1888 or so. So late 19th century. But here's the idea. You have some piece of metal. Okay? And you have light coming in and hitting the metal. Now, the interesting thing part about this is not that the light reflects off shiny metal, which sometimes it does.
So we can't see your screen.
Thank you. The interesting, so yes, light sometimes reflect off the shiny metal. Light will also, heat up the metal, right? Because that's radiation transfer of heat. What's interesting is that when light hits the metal, electrons seem to come off. So you can have what is essentially an ammeter, where you connect one bit of the ammeter to the metal and another to, say, a metal screen over here. So light comes in, hits the metal, electron comes off, hits the screen, travels through the ammeter to get back to the metallic sample, and we measure a current. Getting a little bit fancier, we also put a voltage source in between the metal and the screen here. So from our section on E&M, we know that the potential energy of an electron is determined by the amount, by the voltage difference that it's about to travel across, right? So the electron gets ejected off of the metal with some kinetic energy, and it trades kinetic energy for potential energy as it travels along this voltage difference. And if you increase the voltage that it has to travel across, you'll eventually stop any electrons from reaching the screen. There will be no current. Right? So you can get a stopping voltage. That's what it's called. Another really interesting part of this experiment is that the stopping voltage depends on the color of light you are shining, that is, on the frequency of the light, but does not depend on the brightness of the light. So it depends on frequency, but not intensity. So in other words, the actual rate that you're depositing energy on the metal doesn't matter, right? So more intense light, brighter light is depositing energy more quickly on the metal. But one thing is current happens immediately, right? So this current if the electrons were coming off of the metal just because it was getting hot, because you had left it in the light, then it would take a while to heat up before it started spitting off electrons. But that's not what the experiment shows. The experiment shows that as soon as you expose it to light, you get a current. So it's not heat that's causing this boiling off of electrons. And it's not total amount of energy either, right? So is the stopping voltage, right? So this, which is a way of measuring how much kinetic energy these electrons get kicked off with, right? Doesn't depend on how much light you're shining on the metal, only on what kind of light you're shining on the metal. Anyone having a bit of a headache yet? I stands for intensity, that's right. The third really interesting thing is that there's a minimum frequency. Right? And it depends only on what kind of metal that you've got going. So if you shine light with a frequency below some cutoff, you get no current in this setup at all. And if you shine light with above a minimum frequency, you get current immediately, no matter how weak the intensity of the light is. All right. The last thing that we see from this experiment, if we do it, is actually you know what? I just realized why I was asked if I stood for intensity, because we were also talking about current. We've got some double use of I's here. Yeah, I'm recording. The one thing that intensity does affect is the quantity of current that we detect in this setup. So more light equals more current. And this is one of the things that Einstein was able to explain in 1905 in his Year of Miracles. And today it's called the photoelectric effect. There are a few things that explain these observations. One, the energy in a single photon is proportional to its frequency. And that's why you need at least a minimum frequency to kick electrons out of these metals. Because if your frequency is too low, no individual photon has enough energy to kick off an electron, right? From chemistry, we already knew that electrons are bound to their materials, right? Their atoms. So different materials have different binding strengths, so it makes sense that different metals have different minimum frequencies and thus minimum energies. Secondly, the intensity of the light is actually proportional to the number of photons. So the more intense light has the same kind of photons as less intense light. There's just more of them. So if you have more photons, they can kick off more electrons, which cause a greater observed current. Okay, actually, these are the two main these are the linchpins of the theory that would become known as quantum theory. Today, instead of saying that energy is proportional to the frequency, we say the energy of a photon is equal to a constant h times the frequency. And the h is today known as Planck's constant. Named after the same Max Planck that we just that was optimizing the light bulbs for the German government in that video we just watched. Okay. Questions or comments? Still processing. That's fair. Probably, Nicholas. I think that whole chapter is inbounds. All right, so this is the photoelectric effect. The confusingly, this this minimum energy required to kick an electron off a metal today is called the work function. That's just one of those weird things that we're stuck with because someone in 1908 called it that, and now we call it that forever. Even though it doesn't have a whole lot to do with our modern idea of work. Okay. Today's going to be a video heavy day. Let's watch another one.
We see particle-like behavior every day. Drop a ball on the ground and it follows a single trajectory. Leave your giraffe parked on the street and when you come back, it's still there, just one giraffe. And we see wave behavior too. Toot your horn and waves spread out through the air, carrying sound to the ears of anyone around. Or drive a boat through water and waves travel outwards along the surface. But when it comes to the physics of the very small, what we see is a wave-particle duality. Sometimes very small things, we're talking electrons and protons here, behave like particles, and sometimes they behave like waves, flip-floppers. For example, if you release an electron, it'll travel outward as a wave through the room, but when it hits the wall, it'll only hit in one place. You started with one electron, after all. So what if sound had a wave-particle duality? When you shouted, the sound waves would spread outwards in all directions, but only one person could hear what you said. Or when you drove your boat through the water, the waves would travel like normal, but only hit the shore in one place. Now that would make for some pretty boring surfing. In the last video, I introduced the idea that really small things act sometimes like waves and sometimes like particles. So how can we actually picture this wave-particle duality of, say, an electron? Well, imagine our electron is a speck of dust in a raindrop. We know pretty well where the speck is, at first. But when the drop hits the ground, it'll spread out like a wave, and the speck of dust will be somewhere in that wave. So the speck, our electron, is guided by the wave. But there's still only one speck, and if you actually look for it, you'll only find it in one place. The wave will also tell you how likely you are to find the speck at any one point. If the drop splits in two, you're more likely to find the speck wherever there's more water. And that's pretty much how the wave-particle duality of quantum mechanics works. Each particle is guided by a wave, called a wave function or pilot wave, that determines the chances it'll be in a certain place or state. Easy, right? The hard part is figuring out the movement of the waves.
All right. There's a lot of heavy conceptual stuff in this chapter, which is why I'm trying to break it up with some videos. And there's a lot of kind of mind-bendy stuff, right? Like it was hard enough learning to think of things as waves when we're used to, on the macroscopic scale, dealing with particles. But just as soon as we break our minds enough to think of things as waves, now we have to think of them as particles again and at the same time. So there's a lot going on. Alright, one thing that you may have covered in chemistry, in fact you should have covered in chemistry, author has a question. How about super small stuff? Does this apply to them too? Yes, and even more strongly. So, the smaller it is, quantum mechanics applies to everything. It's just that for things that are big, quantum mechanics is approximately classical mechanics. Right, what you learned in 151. And for the really small stuff, things that are smaller than an atom, they're not even approximately correct with classical physics. Like, classical physics doesn't even begin to accurately describe the super small stuff. And things like muons and quarks, we don't necessarily have particle confirmation of them. Like, we didn't think they existed until we started analyzing the waves. That's not an entirely complete explanation, but also that's a 40-year journey that we went on as to discover that muons even existed. All right. So one thing that you may have done in chemistry is draw some energy level diagrams. So you were probably introduced to the idea that electrons, so we have a nucleus, and then we have electrons in orbitals around the nucleus. And they aren't allowed to have any amount of energy they want. They're only allowed to have certain energies. And we usually denote this with, if I could draw straight lines. we make an energy level diagram. To say our ground state is, say, here. This is the lowest energy state that electrons in an atom can have. If somehow they get excited, and by excited we just mean they absorb some energy, maybe from a photon, maybe because you ran electricity through it, maybe just because it's really hot. But there are other levels of energy that the electrons are allowed to have. So let's say we are down here to begin with. And some light comes in, and this is light that's below the minimum frequency to kick the electron out completely. That is, the photon has less energy than the ionization energy of this electron. So light comes in, and even though it's not going to kick the electron off completely, like in the photoelectric effect, it's going to, say, give it enough energy to move up here. All right. So nature hates having things with more energy than they absolutely need to have, right? So the lower the energy, the more nature prefers that things hang out there. So eventually, and usually on the order of nanoseconds rather than anything longer, this electron will mosey on back down, and then maybe also come all the way back to ground. So if you remember from chemistry, what happens to the extra energy that the electron absorbed to get up to this high level? So when it you're close, Nick. You're close. Light, yes. And of course, radiation is one way for heat to get transferred out of an object. But yes, what comes out of here is light. And not just any light. Light with exactly as much energy as the difference between these two allowed energy levels. So that means, in principle, that if we want information about the energy levels of an atom, one way to do that is to excite it in some way, electricity, heat, whatever way we want to do that. And then we see what colors it gives off as the electrons decay back to lower energy levels. And these colors are going to be directly determined by how much energy there is between the level it started with and the level it ended with. And that observation actually goes back to the 1890s, right? So this sort of spectroscopy was being done by astronomers in the 19th century. So before we had any idea about quantized light or quantized energy or quantized anything, we could observe it, we just couldn't explain it. If you were in person, you have an in-person lab, you're going to do a really cool demonstration experiment to this effect. For those of you who are not in an in-person lab, I have another video to show you.
This is one of our funnest demonstrations to show atomic spectra. I'm going to show the spectrum of an incandescent bulb, which is continuous. And then I'm going to show the spectra of 4 different elements. mercury, nitrogen, neon, and especially hydrogen. Hydrogen will be important in the labs and in many other applications. So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. So it's called a grating, just like a street grate. It has lines through it. And this allows you to resolve the spectrum of a source of light. In the
We covered this 2 weeks ago, right? So the spacing of a diffraction grating determines what angle the light will be diffracted at, and different colors of light will be diffracted at different angles.
same way that a prism will resolve a spectrum. So what we're going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with the diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left you'll see a rainbow spectrum that shows what wavelengths are present in this. You'll see, as you look on the right side, violet through all the colors of the spectrum all the way through red. So that's a continuous spectrum. We'll try next to look at a discrete spectrum of mercury. Now what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using.
He's actually underselling it here. This box that he's putting it into produces 5,000 volts, and that pumps a lot of electrical potential energy into the mercury vapor inside, and then when the electrons relax to a lower energy state, we'll see some spectral lines come out.
In this case, mercury. So I'm going to locate this its proper spot, turn off the continuous spectrum. So this is a mercury spectrum without the diffraction grating. And let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum. Next we will try a
Not pictured, the strongest emission of a mercury vapor is actually in the ultraviolet. So of course we can't see that with our naked eyes.
A nitrogen spectrum. I'm using this fur to prevent burning flesh. So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. That's nitrogen. Two more. This is neon. There's a beautiful
We're all
orange look
familiar
to
with
it,
neon.
and when the diffraction grating is in place, you see a large number of red and orange lines. This is exactly what's used for neon lights. The original neon light was made out of neon like this. There are other gases that are used to form signs, but neon was really where it started off. It has a beautiful, bright, reddish orange spectrum. So this is hydrogen. It has a reddish cast to it, and when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line. And it is very important in star images. A lot of nebula in the sky have hydrogen alpha line as one of their prominent spectral lines. Then there's a turquoise colored line. Greenish blue is the hydrogen beta line, both from the Balmer series, and we'll talk about those, or have talked about those in class.
We won't.
And then finally, the hydrogen gamma line is a violet line, is generally considered to be the one that's, those three lines are visible in the hydrogen spectrum. Those lines are associated with transitions of the electron in the hydrogen atom from a higher state to a lower state. In this case, the second energy level is the final state, and then higher energy levels, it starts from a higher level and goes down to the second energy level to get the Balmer spectrum. That is continuous and emission spectrum.
That's pretty, right? It's cool.
Very.
Yeah, in an in-person lab, you would have gotten to do that yourself.
So when he showed the light and the gradients on it, and it showed all the colors in the spectrum, I'm assuming there were also the rest of the higher and lower energies of the spectrum, like X-rays and
You mean on the first one with the incandescent?
yeah.
Yeah, there's significant amounts of infrared light from an incandescent light bulb, small amounts of UV light, and then not really any X-rays. It tapers off pretty quickly as you go to higher energies.
So if we could see higher and lower energies on the spectrum, we'd be able to see more than just the visible light spectrum.
Well, yeah. You mean if we were mantis shrimps?
Yeah.
I have often thought of that myself. All right. So
Fascinating.
that kind of demonstration is, I think, pretty clear evidence for the energy levels of electrons in atoms, right? So like that observation that we make is why we say that electrons can't just have any amount of energy. They can only have, like, the difference in energy of their energy levels has to be equal to the energy of those colors of light that we see when they're falling back down. And if you have ever wondered, hey, why do we know that the sun is made out of hydrogen? That's why. Because you put a diffraction grating on your telescope and you look at the sun and you see those lines. All right. Let's do one more one more thing before we take a break. So how many of you remember studying conservation of momentum in Physics 151?
A little bit.
So, does everyone remember Newton's second law? So Newton's second law, force equals mass times acceleration. And by acceleration, we mean change in velocity over time. So we can do a little rearranging of this thing and say F, the force times a change in time, equals a mass times a change in velocity. And if mass is constant, we might as well just do a little trickery like this. The change in mass times velocity is equal to a force times the time. And this thing here, we call this impulse on the left-hand side. And this mv, we just call that momentum. So one way of writing down Newton's second law is that impulse causes a change in momentum, right? No impulse means no change in momentum, and this is what we use to study collisions. So think back to the photoelectric effect, right? Photons come in, knock electrons out of the metal. Electrons move over and hit the screen to the right. If the electrons are moving, that means they have momentum, right? But if they have momentum when they came out of the metal, where did they get that momentum from? Right? Because when they're in the metal and they're just hanging out, doing their electron thing, they're not going anywhere on average, so they have no momentum. But when they get kicked out of the metal, they do have momentum. So where did that momentum come from? No one wants to guess? Yeah, that's right, Nicholas. It had to have come from the photon, right? So if electrons are getting kicked off with momentum, it must mean that the photons brought in momentum. But that's a little weird to think about, right? Because we defined momentum as mass times velocity. And what's the mass of a photon? What's the mass of a particle of light?
I have it in my notes somewhere. It's very, very small. Like negative 39? 10 to the negative. I can't remember.
It's actually 0. Photons don't have mass.
Okay, I'm thinking of protons. I believe you.
They are pretty light. Oh man. We got this far in with no puns, and now... Okay. Yep, they are pretty light.
You came up with that joke pretty fast.
I think that he was holding on to it. Yeah, that's reminds me of my favorite pun. What's the difference between a Zippo and a hippo?
One is lighter.
Yeah, well, Zippo is a large mammal, or hippo is a large mammal, and Zippo is a little lighter. So yeah, photons have no mass, but they must have momentum because they gave it to the electrons in the photoelectric effect. So that actually leads us to think, well, maybe we need a bigger, more general idea of what momentum means, right? And there is some background for this. So last class, we talked about the relativistic energy of a particle, right? So I'm going to use a different color. The full relativistic energy of a particle squared is equal to p squared c squared plus m squared c to the fourth. Does that look familiar? Maybe. I know that last week was a lot. Okay. This gives us two special cases of energy. So for non-moving, we just get E equals mc squared, which I assume all of you have heard at least once. It's slightly famous. So if you have no movement and thus no momentum, then the energy of an object is what's called its rest energy. It's mass times the square of the speed of light. The other special case is massless particles, like light, in which case you just get E equals pc, right? Speed of light times the momentum. And this is how we end up defining momentum for light. The energy of a photon divided by the speed of light is the momentum of that photon. From our examination of the photoelectric effect, we know that the energy of a photon is equal to its frequency times some constant. So if we plug that in for E here, we get this constant, Planck's constant, times the frequency divided by the speed of light. And then one more simplification. We remember that for any wave, the velocity of a wave is equal to the frequency times the wavelength. So instead of writing F over C, usually we write Planck's constant divided by the wavelength. And this is a way of writing down the momentum not of a particle with mass, but of a wave with a wavelength, which is kind of wild. But that's how we deal with the momentum of a photon. Now, this comes a little bit later than our 1915 cutoff, but what if you solve for lambda with this relationship, where you can say lambda equals Planck's constant divided by the momentum? And actually, this is what we call the de Broglie wavelength. Right. So the de Broglie wavelength, just like we started off looking for how we could define the momentum of a photon, and we found it, but what we ended up with was a way that we could define the wavelength of a particle. And this is, in fact, how we define the wavelength of things like electrons, protons, neutrons, baseballs. It's pretty wild stuff. So velocity is not in the numerator. No? I guess I don't understand what you're asking there. Oh, forgot about C. Yes. All right. So a quick roadmap. This is what we did in the first half of the class. Photons have particular energies, which are dependent on their frequencies. Electrons can only have particular energies. Not only that, but photons must have momentum, and particles also have wavelengths. It's kind of a wild ride we've been on. We have any questions before we break for a leg stretch?
When you say electrons have particular energies, what do you mean by particular energy?
Like, they can't have just any amount of energy, right? So when we did 151 and you solve for, like, what's the kinetic energy of a train, going up a hill, it could be any number, right? It could be 14, it could be 14 and a half, it could be 15 joules, it could be 1,000 joules, it could be 100, like, whatever number, right? By tuning, the how high the hill was or whatever, you could end up with any number for energy you want. But electrons aren't like that. They can only have a few particular quantities of energy. So like in the ground state of hydrogen, right? There's one electron, right? So one proton and one electron. And the energy of this system is equal to minus 13.6 electron volts. We know that because that's how much energy it takes to ionize hydrogen. And that's the same for every hydrogen, right? So all hydrogen in their ground state has, a binding energy of 13.6 electron volts. That's the only energy that a ground state electron in a hydrogen atom is allowed to have. If you excite, if the electron gets excited via electrical stimulation or thermal stimulation or whatnot, it can jump up an energy level, but it can't jump to any energy level. It can only jump to, I think, this is now negative 9.8 electron volts. I might have to look up that number. But it doesn't get raised to just any number of energy. It gets raised to a very specific amount of energy. Right? And then if it goes, so this is ground state, first excited state. There's also second excited states. Then there's more excited states, and each one of them is closer and closer to the previous one. But the idea is it can't just be any amount of energy. In fact, there is a famous formula for describing this energy, and it was alluded to in one of the videos we watched, although we don't we're not going to cover it too explicitly, but it's called Balmer's formula. And I'm just going to pull it off Wikipedia real quick. But this tells you what values you could possibly get for a wavelength. That you could possibly see for a wavelength in hydrogen. Right here, n is equal to 2, 3, 4, etc. Any integer above 2. Did that answer your question at all?
Yes, thank you.
Okay. All right. So with that, let us take a short break to stretch our legs. I have 1:06 on my clock right now. Let's come back here at 1:15.